Good morning and welcome everybody to the CMSA Colloquium for this week. Today we have Professor Piotr Sulkowski from the University of Warsaw. He will tell us about strings, knots, and quivers. So let's welcome Piotr.
Okay, thank you very much for the invitation. So in my talk, I will give an overview of some activity. The title Knots and Quivers has been developed in the last few years by me and also some collaborators and also some other groups. So I understood that I should be a bit general, so I try to be a bit general. And well, the relation between knots and quivers in our setting arises from some string theory motivation, which I will review. But it also makes contact with other areas of physics and mathematics, such as Gromov-Witten theory, 3D supersymmetric gauge theories, some lattice path problems, some areas of combinatorics. In particular, you will see that the objects called Perimutahidra arise in our consideration. Topological recursion, the theory of Q-hypergeometric functions, and some relations to number theory arise. So I hope that for some of you who work on different topics, at least some aspects of what we are doing might be of interest. And I will start with the string theory motivation and then mention some of these connections later on. Let me just say that the talk is based on these two. I mean, our story started from these two papers, which already have 4 years, but it is still being actively developed. But as a starting point, you can look at one of them. The top paper is a short one, just a brief summary, and the bottom one is much longer and has much more details. So, as you probably know, in general, when you consider the string theory, it quickly turns out that we expect that there are 10 dimensions. 4 of them should represent our space-time, and another 6 are compactify on a Calabi-Yau manifold. And the challenge in the full string theory is to devise such a Calabi-Yau manifold, which would give rise to standard model theory or maybe some supersymmetric generalization of it in these 4 dimensions. So this is what usually string theories do, and of course this is a hard task. However, there are interesting toy models of this activity which are lower dimensional, and they are easier to deal with and lead to various deep statements in mathematics. And these models are based on usually 6-dimensional so-called M5 branes, which are then compactified to lower dimensions. So one example of such activity is known as the Alday-Gayotto-Tachikawa duality. And in that case, you compactify this 6-dimensional theory on a 2-dimensional Riemann surface. And you end up with a theory in 4 dimensions, which is some supersymmetric gauge theory. And some of its properties are encoded in this 2-dimensional surface, in particular in 2-dimensional CFT on the surface, and amplitudes in Liouville theory or Toda theories. So this is one example of such relation. Another example in other set of dimensions is referred to as 3D correspondence. In that case, we take this M5 brane theory and compactify on 3 manifolds to get some supersymmetric theory in 3 dimensions on one hand. And their properties are captured by some topological invariants of this 3 manifold that we used. In particular, these invariants can be obtained from Chern-Simons theory, and also this makes contact with knot invariants. Yet another possibility is to compactify this 6-dimension on some 4 manifold. In that case, we again obtain supersymmetric 2-dimensional theory, whose properties are somehow related to properties of 4 manifolds. So for the purpose of my talk, this middle line is relevant. And what we are interested in are certain relations between supersymmetric theories in 3 dimensions and free manifolds. And this is also why knots somehow appear. So I will focus on more or less this, this perspective. I will give some details soon. And let me just quickly sketch, I'm sure you are aware of that, but just to set up the notation, the reason that Chern-Simons theory arises in connection with knots should be familiar, namely Chern-Simons theory as a topological quantum field theory. The relation to knot theory was shown by Newton in the seminal paper from '89. And from this perspective, knot invariants arise as expectation values of Wilson loops. In particular, Hom-Flippity polynomials appear when we compute expectation value for Chern-Simons theory with SUN gauge group, and we have to make appropriate identification of parameters. So Hom-Fli knot polynomials depend on these 2 parameters Q and A, and they are related to the rank of this gauge group N, and also the level denoted by K, which is the coefficient in front of the action in this path integral above. And as you probably also recall, in knot theory, we can get various types of knot polynomials. From Hom-Fli polynomial, you can obtain Jones polynomial by specializing A to BQ square, which means that we take just a SU2 gauge group. We can get Alexander polynomial where we set this small parameter A to B1 and so on. So this is a familiar picture. This is how knot invariants are related to topological quantum field theory. But what is more relevant for us is that this relation can be embedded in string theory, or to start with, in topological string theory, which is a theory that needs 6 dimensions to where it should live. So the way to obtain the 6 dimensions is to take cotangent bundle T star as free with appropriate boundary conditions. And as Witten showed in 1993, in that case, A-model amplitudes in this topological string theory agree with amplitudes in Chern-Simons theory. So this is one fact which is important. And this is also important that this T star as free, this is the manifold also called deformed conifold. It can be regarded as the deformation of singular conifold, whose equation is shown here. And this singular conifold can be also deformed or resolved in another way, in such a way that instead of S3, we get S2. So this whole process is referred to as geometric transition. You can, in fact, think of starting with this deformed conifold with S3, shrinking this S3 to 0 size, and then resolving into S2. And if you consider string theory on this manifold, also something interesting happens to strings or branes, which impose these boundary conditions I mentioned earlier on S3, namely they disappear. And in this right-hand side, in this resolved conifold setup, we are left with closed topological string theory. So this process is referred to as open-closed transition also, and it was clarified and discovered by Gopakumar and Vafa in 98. A consequence is that the Gromov-Witten invariants computed for the resolved conifold geometry turn out to be related to Chern-Simons invariants that we started with in this deformed conifold geometry. And the closed topological string partition function that is schematically shown here in the bottom has the characteristic genus expansion And these different Chern-Simons invariants are related to this free energies, topological string free energies Fg. So this is the setup where knots do not appear yet. However, it is also possible to encode information about some knot by choosing appropriate Lagrangian brane in this initial T star S3 geometry. This brane is chosen in such a way that it intersects S3 along a particular knot we are interested in. And then certain knot invariants computed by this open string theory on left-hand side, or Chern-Simons theory, are also captured by topological strings, this time the open version, on the resolved conifold. So this brane, which encodes the knot, it survives this geometric transition, and then it is still present in the setup on the right-hand side. So this is more or less the setup that we need to have in mind. And moreover, this setup can be also embedded in 10-dimensional superstring theory, or even M theory, which is 11-dimensional extension of superstring theory, in such a way that as a space-time, this full 11-dimensional space-time, we take R, or sometimes S1, times T star S3 that we started with, and then for manifold that is supposed to be our space-time, you can think of just R4 in this case. Then those branes which we earlier wrapped on S3, in this case, become part of M5 branes, and they wrap S3 and R and 2-dimensional subspace, let's say just R2 of this R4. And in addition, the M5 branes, which encodes a knot, wraps this Lagrangian brane that I also mentioned, and R, and the same 2-dimensional subspace that I just mentioned. So this is the situation before this geometric transition in this setup, which involves T star S3. We can also consider geometric transition. In that case, we end up with a resolved conifold, which I denote by X this time in this second, in this middle part of transparency now. And those N M5 branes are gone, as I also mentioned before. However, we are left with this M5 branes, which encode information about the knot. They still wrap R and this Lagrangian brane LK. Here L states just for the Lagrangian, and K in the subscript refers to the knot that we consider. And then they still wrap this 2-dimensional subspace of M4. So this picture, it's important because, among others, it enables to relate some knot invariants of this knot K, originally computed by Chern-Simons theory, to certain so-called BPS invariants. In particular, they need to be integers, so this is quite an important property, which can be thought of as characterizing some effective supersymmetric theory on 3-dimensional space R times D.
May I ask a quick question? So you denote the Lagrangian after geometric transition again by LK, but this is something different, right?
I'm not sure I understand.
So before you have this LK,
yes,
which is some Lagrangian. After geometric transition, it should become something different, right?
Well, at infinity, it is the same. It indeed may look a bit different, like at the core of this conifold.
I see.
So I think in some special cases, it is described explicitly what happens to that, at least for some knots.
I see. And but they always exist for any LK when, like,
at least I think I'm not sure if there is proper mathematical proof, but it is conjecture that it always. I mean, the Lagrangian before the transition, of course, always exists. This is a normal brane to a knot. So
yeah, so yes.
After the transition, I cannot. promise there is mathematical proof what happens to that. But for sure, it is understood at least in some special cases, like torus knots.
I see. Thanks.
Okay. So these BPS numbers, which I just mentioned, they appear in the following way. This is some simplified formula. Let me just say that in this case where we consider the situation with a knot, we can compute its Humphrey polynomials, which are represented by this P with index R here. These are colored Humphrey polynomials. They depend on A and Q. And we can form some generating function of them, with X being a generating parameter. And then the consequence of this geometric transition is that this generating function can be written in this product form, where you can think of this product as a product of quantum dilogarithms. In particular, this product over K gives the structure of quantum dilogarithm when we fix R, I, and J. And these BPS invariants arise as exponents in this expression on the right. So the statement is that they are integer and they can be expressed in terms of these Humphrey-Petit polynomials. Let me also show you maybe in a bit more detail how this relation follows, and also a bit more generally. So again, in this top frame in this slide, I have a generating function of colored Humphrey polynomials, but now they are colored by arbitrary representation. So this index R denotes arbitrary Young diagram here. In the previous slide, I had just small r, which denotes, in this case, a symmetric representation, which is a Young diagram, which is made of one row, which has R boxes. But one can be more general. So the conjecture by Oguri-Waffa, or Labastida, Marino, Oguri, and Waffa is that this generating function can be written in this exponential form with certain functions f, also with index r. And these functions have this special structure as given now in the second frame, where this capital N are this integral invariants. And if you work with this expression a bit, you can rewrite this f in terms of Humphrey-Petit polynomials, like in this example, where for the third symmetric representation, you can, here I expressed f in terms of sum of Humphrey-Petit polynomials. And of course, this is quite a non-trivial statement that this particular combination of these polynomials has such a structure as f should have. So in particular, it has a very simple denominator, q minus q inverse, and it encodes all these integral numbers. And when it is possible to specialize just to symmetric representations, in fact, I will consider them in the rest of the talk. And in that case, this exponential form can be written in this product form that I had in the previous slide. So the fact that these integral numbers exist was conjectured by Oguri-Waffa, Labastida, Marino about 20 years ago. And for some time, it was not proven. In the very beginning, people just checked in various examples by considering some specific representations that integral numbers arise, but it were just numerical checks up to some order. So one of our interests in the rest of the talk are these integral numbers, and it turns out that to get them, this relation to quivers is useful. So I will present now this relation to quivers. We refer to this as knots-quiver correspondence. And of course, all this introduction which I made so far is, I hope it will be helpful, because whatever I will talk about will be based on that physical picture that I just presented. So the statement of this knots-quivers correspondence is that these BPS states, which I just mentioned, which appear in this LMOV formula, are in fact bound states of certain elementary states, and their interactions are encoded in a quiver diagram. So in this picture, this is one example. On the left side, I have trefoil knot, and on the right side, I have a quiver which corresponds to this knot. I can tell you later how we found this quiver, but the bottom line is that the nodes of this quiver correspond to these elementary states. The arrows somehow to the way these elementary states may interact to form bound states. And then there is some partition function associated to this quiver. You can think of it as the partition function for a quiver supersymmetric quantum mechanics in this effective theory. And this partition function agrees with generating function of Humphrey polynomials, or in other words, with topological string partition function in the setup where this knot arises, or where this knot is encoded in properties of some Lagrangian brane. So just to say a few more details, let me give a very brief overview of quiver representation theory. For mathematicians, when you see a quiver, you probably think of some vector spaces associated to the nodes, and then linear maps between these spaces which correspond to arrows. And mathematicians are interested in properties of moduli spaces of such representations, which are characterized in particular by so-called motivic Donaldson-Thomas invariants, which are roughly speaking dimensions of various homologies associated to these spaces. And well, I don't want to present this theory in detail. I'm first of all not an expert in that theory, and also we don't have enough time. So just one important result that I need is that to get this motivic Donaldson-Thomas invariants, one may construct so-called quiver generating function given by the first line in this formula. So this is this line, the summation. And then the statement is that this line can be written in the product form. And then these motivic Donaldson-Thomas invariants arise as exponents in this second line. So this quiver generating function is crucial for us. At first sight, it might seem complicated, but it is not so complicated. You see that this is the summation such that in numerator we have q raised to a power which is quadratic in the i's, and the coefficients of this quadratic form are entries of a quiver matrix. So the Cij, these are numbers of arrows between vertex I and vertex j in a quiver. So the whole information about a quiver is just here in this quadratic term. And then in the denominator, we have q Pochhammer's q square, d1, and all of them up to the m, where d1 up to the m are summed over. These are sums associated to each of the nodes. So there are as many summations as the number of nodes in a quiver. I denote this number of nodes by small n. And then there are also some generating parameters x1 up to xn, also raised to the powers d1 up to dn. So
could you remind us what's the meaning of this J in the subscript of capital omega?
The meaning of J?
Yeah.
Well,
in capital omega.
This is this motivic parameter.
So it's an integer?
This is integer. You see this in this middle product. Physically, it corresponds to the spin of particles, as you will see. So you will see that these omegas have something to do with these BPS numbers, and in the quantized version, you need to keep track of their spin. So For physicists, this is what it labels.
I see. Thanks.
Oh, sorry. Can I ask a quick question?
Yes.
So, is there a way to get this definition from like Kontsevich-Selbelman's definition for motivic?
Exactly. Yeah. So in particular, yeah, this relation appears in the work of Kontsevich-Selbelman, and in fact they conjecture that omegas are integer, and later it was proven by Efimov that indeed they are. In fact, they are positive integers. It is also important, I should have stressed that these quivers that we consider, you might have guessed if you look carefully, they are symmetric, which means that if you have an arrow from vertex I to vertex j, you must also have the arrow in the opposite direction. So this is the situation where this proof by Efimov holds, and somehow this is crucial for us as well. I mean, all quivers that we find are indeed symmetric, so this result is very useful for us.
I see.
And okay, so now the reason I mentioned this relation and this quiver generating series is that its structure, if you recall this generating function in Oguri-Weffa form, it's very similar to that one. So in particular, the way these omegas appear is quite analogous to the way these BPS invariants appeared in that Oguri-Weffa formula. And it turns out that indeed you can identify both of these formulas if you make appropriate change of variables. And this is the statement of knots-quivers correspondence. Namely, if you make appropriate identification of variables, then the generating function of colored conflict polynomials with appropriate normalization can be written in this form of motivic generating function for some particular symmetric matrix C. So this is what is given in this formula. On the left side, I have analogous generating function of conflict polynomials as I had before with this generating parameter x. On the right-hand side, I just have the quiver generating series, which I just mentioned. I just specialized those x's, those different x1, x2, up to xn, to some specific form in such a way that each of them involves x, and then I have a, q, and -1 raised to some linear powers. I mean, this ai, li, and ti, these are some fixed parameters. They also have some clear interpretation, and we essentially know what they are. And then in the formula, they are raised to the power di, so this is just linear powers of d. So this is quite a non-trivial statement because it tells you that all these different colored conflict polynomials are essentially captured by this matrix Cij, which now you can think of as matrix defining some quiver. And in addition, a few of these extra parameters, li, ai, ti, which we also know. So this is one important consequence of this relation. And then there are other consequences, or you can look at both sides of this relation between knots and quivers, and you can realize that some objects on the knot side correspond to some objects on the other side. For example, the number of loops in a quiver. By loops, I mean arrows which start from one vertex and go back to the same vertex. The number of loops corresponds to so-called homological degrees. I will also mention soon what this means for a knot and framing. What I already mentioned is that this quiver motivic generating series corresponds to generating series of colored conflict polynomials. And then important consequence of that is that through this relation, we can relate motivic Donaldson-Thomas invariants to this BPS invariants or LMOV invariants. And now the crucial statement is that these motivic DT invariants are non-negative integers, as we already discussed. Because this means that if we can relate them to this LMOV invariants, we conclude that LMOV invariants must be also integer. And this is so for all of these invariants, it's infinite family of them for a given knot. I mean that if you have a knot and we find the corresponding quiver, it automatically means that all these LMOV invariants must be integer because we can express them as some combination with integer coefficients of this dt invariants. So this is one of the most important conclusions of this relation. We can also specialize this motivic invariance to so-called numerical invariants. This is, roughly speaking, the limit when q goes to 1. And in that case, there is also classical version LMOV invariants, which are related to this numericality invariants. And there are other relations. I don't list all of them. Well, one of them is that on this quiver side, there is so-called homological whole algebra, which is also considered by Kontsevich and Seipelman. And it can be identified with algebra of BPS states, whose existence was also postulated many years ago. By streets, we can make this relation precise. So this is this relation. That is the main topic of my talk.
Oh, sorry, can I just ask a question?
Yes.
Oh yeah.
Sure.
So just go back to the previous question you just mentioned, like the quivers you find are all like symmetric. Is that related to some Calabi-Yau condition?
I'm not sure. It is a bit mysterious, at least to me, I think, why they should be symmetric.
Isn't it true that it's symmetric because there's an extended supersymmetry? And maybe one can relate this to Calabi-Yau condition.
I see.
Yeah, I'm not really sure, but that's a good question, of course.
Yes, I see. Thank you.
Sure. Okay, so maybe I can, well, I give some examples in a moment, but in fact, I should mention one more point, which is also important, because whatever I mentioned so far is about Humphrey, I mean, not only, but on knot theory side, this Humphrey polynomials played prominent role. But it turns out, and it is also quite a big surprise, that these quivers that we find, they know something about knot categorification, or so-called Humphrey PT homology, which is some hypothetical homology theory, which in principle should generalize, for example, Kovanov homology. So Kovanov homology, of course, is defined rigorously, and then there is also Kovanov-Rożański homology, which is defined rigorously for SLN, not invariants. But it is like conjectured or believed that there is also further generalization, which is called Humphrey PT homology. It does not have a proper, as far as I know, mathematical formulation, but there are certain conjectures how it should look like. In particular, there are some structural properties which have been conjectured it should have. And from these structural properties, one can deduce some information. In particular, one can deduce what should be the form of so-called super polynomials. So super polynomials are generalization of Humphrey polynomials, and they are expected to have such a property that Humphrey polynomials arise as their specialization when you set some extra parameter they depend on, which is denoted by t, to be -1. So in the first line, you see that this Humphrey, more general colored Humphrey polynomials are expected to be specialization of, well, are expected to have this form, that they are sums of a and q to some powers with extra sign to some power with coefficients which are dimensions of these homological spaces we expect to exist. And more generally, you can replace this -1 by t and then obtain super polynomials, which are polynomials with positive integer coefficients, which capture some information about this Humphrey PT homology. And in particular, as it usually happens in this specialization of t to be -1, some of the information of this homology can be lost, because when you go to Humphrey polynomials, we get some cancellations. So certainly those super polynomials have some more information than just Humphrey polynomials. And just to give one example, so that you have some idea how these objects look like, we may focus just on the so-called uncolored case, which is the case when the small index r is equal to 1. Then we talk of uncolored super polynomial. For figure 8 knot, it has structure as given here, this P1. It has 5 terms. You see it starts with a inverse t to power -2 and so on. And this is indeed a polynomial with positive coefficients. And each of these coefficients corresponds to one homology generator of this hypothetical homology theory. And this is useful to draw these generators on a diagram in such a way that powers of A and Q correspond to the vertical and horizontal axis. So the dots in this diagram and are in the positions which encode power of A and power of Q of the corresponding term in this super polynomials. And these lambdas, they correspond to this change of variables that enters in this knots-quivers correspondence. So in knots-quivers correspondence, I mentioned that xi are fixed to be x times some monomial in AQ. Previously I said -1, but in fact you can generalize it to this super polynomial case. So we can also include t there, and they are raised to the powers, which are the powers of A, Q, and T in these uncolored polynomials. And furthermore, so now this crucial point, this relation of this homology theory to quivers appears in such a way that on the diagonal of this quiver, this diagonal entries CII are equal to the powers of T in this uncolored polynomial. So again, in this P1, you see you have these terms A-1, T-2, and then T-1, Q-1, and so on. So the powers of T are respectively -2, -1, 0, 1, and 2. And these are precisely the terms which you find on the diagonal of a quiver. So this is one manifestation, then this quiver knows something about non-homologies, even though this is not the information that we put in any way. It comes out like a magic from that. So yeah, this is one property. I will probably, hopefully, go back to that also in what follows. But before that, let me just show you some examples how it works. So we can reconstruct these quivers in particular in situations when we have explicit formulas for colored polynomials. And we have them for various knots. For example, for trefoil, it is known that this colored Humphrey for arbitrary color has the following form. You see that this is expressed in terms of some Q binomials and Q-hammer. So if you play with this formula, this is how we started our work on that topic, in fact, you may realize that this Q binomial times this product, which is a Q-hammer, you can rewrite in the following form, but using so-called Q binomial theorem. You see that if you use this formula, you obtain the summation in the denominator, you get 3 Q-hammers with some indices, and then if you play with this summation indices, you can put it in the form of the quiver generating series. And then you find what is this corresponding quiver, which is that's given here. I mean, you find this quiver matrix, which I showed. This is symmetric, which corresponds to the fact that quiver is symmetric. And then it must encode this quiver, which I already presented above. So if you know how those colored polynomials look like, with some effort, of course, for more complicated knots, you need more effort, but you are able to reconstruct the corresponding quiver. So this is another example for 2,5 torus knot, or in other words, 5,1 torus knot. and so on. You can repeat this exercise for various other knots. So here is the example for torus knots 3, 4, 3, 5, 3, 7. This is 6, 2 knot. This is 6, 3. You see, these results are already quite non-trivial, because for 6, 2 and 6, 3, the size of the quiver is respectively 11 or 13. So this is hopefully quite non-trivial that this quiver matrices encode all these corresponding colored polynomials. And this is also quite non-trivial that, as I mentioned, on the diagonal of this matrix, you get this homological T degrees that are encoded in this homological super polynomials. So, well, just to sum up, in the follow-up work, I mean, in the last couple of years, the existence of these quivers have been proven in various cases. I mean, in the initial work, we proved it for some, for all knots up to 6 crossings to start with, and then some families of torus knots and twist knots. And more recently, it was proven by Marko Stosic and Paul Wedrich at first for all rational knots. So this is quite a non-trivial infinite family of knots. And then for yet more complicated arborescent knots and links. This definition of arborescent knots is quite, well, it's not something I can say in one sentence, but essentially this is a very big family of quite complicated knots. So this is already quite non-trivial set of knots for which it holds. Okay, so this is a summary of this knots-quivers correspondence and some examples. And then in the rest of the talk, I would like to mention some related topics or related to these different areas of mathematics or physics I mentioned in the beginning. Just maybe before I do that, maybe that's a good moment to ask some question if you would have any other one. Okay, if not, then I try to say a few more results. So the first one, it might also sound a bit surprising, but it turns out that this relation to quivers is also related to the counting of lattice paths. So I hope it might be of interest to someone. Namely, there is a class of problems which are in some sense classical, but they are still not fully solved. And we were able, by making contact with these quivers, to shed hopefully some new light of them and solve some of them. So this classical problem I'd like to mention is such that you draw a line on the 1/4 of a plane. If it has rational slope, it goes through some integer points, like in this example. And if you fix some of those points, you would like to count, first of all, how many paths which start in the origin and end in a given point exist. And these paths can be made only of the steps which go either to the right or to the top. So one such path you see here. And you would like to know the number of those paths for any of these integer points. So you want to make such a generating function as given in this formula. So here k denotes the number of the point you are looking at with this integer coordinates. And then coefficient given x to power k should be the number of paths that you want to find. So if a line is just y equal x, the slope is 1, then these numbers are Catalan numbers. If the line has slope 2/3, then we get so-called Duchamp paths, and the generating function is shown here. So you might have heard of that as well. If the line has rational slope r over s, then the number of these paths can be obtained from so-called Beasley formula. So this is something that is already known. However, it was not known, to my knowledge, what is, first of all, Q deformation of this result. So apart from counting the number of paths, you can also associate the area between this line of a given slope and a given path to a given path, and you can Q deform this generating function that I just mentioned. And we found that these generating paths have something to do with torus knots, first of all, and second, with quivers which correspond to those knots. So this statement is given as proposition 4.2 in this paper, whose archive number is given in the bottom. And yeah, the statement is that the skew-deform generating function for a given knot is given by the ratio of this Comfley PT generating function or corresponding quiver generating function with appropriate specialization of this xi parameters. And of course, we might forget about quivers and have just this relation to knots. The important point is that if you have a line of a slope r over s, then the corresponding knot that you need is the torus r, s knot in some special framing, which is r times s. So you might be happy just with this relation to knots, but in a sense, the relation to quivers is even more interesting because you get information about this generating function of paths. I mean, this information is encoded just in this quiver matrix. So there is finite number of data that you need. And also we have some more explicit expressions from this quiver side, which we can use. So for example, this quiver matrix is relevant for torus knots of type 2, something, 2, 2p plus 1 are given here. Some explicit examples you have in the bottom. And indeed, here are some explicit results. So starting with the trefoil, just using this relation I just showed, we get this skew-deform generating function, which encodes all these area-weighted paths. And for q equal 1 be-reproduced Dushan paths, and also some non-trivial identities which are relevant for them. So the number of Dushan paths for a given n, which means Dushan paths of length n, is given by these formulas here. And more explicitly, again, in the bottom, there is this classical Dushan formula. And you can repeat this for other torus knots. For 2,5 torus knots, you have the result here. We can write down the result for arbitrary 2, 2p plus 1 torus knots. And so in this area, one important puzzle was, in fact, yeah, this is quite non-trivial, even though the problem is simple. The solution of these problems is not that simple, and it was not known what is or how to write explicitly the generating function for line of the slope 3/4, 3/4. So from this relation to quivers, we can immediately write what is this generating function. It is given in this way. There is some coefficient in this formula, which I didn't even type because it is a bit complicated, but I just would like to give you the message that we can solve these problems explicitly. So this is one of the relations and applications of this knots-quivers correspondence, which hopefully might be interested to someone who is interested in this type of statistical problems. Yeah, so as you see, now I'm maybe quite fast. I just want to mention most important results and somehow advertise various connections. So another connection is to another combinatorial structures, which are called Perimutahidra. And this is something we discussed in a recent work from May this year with my collaborators, in particular a few students. And this relation to this combinatorial structures called Perimutahidra arises because it turns out that in fact these quivers that correspond to knots are not uniquely defined. And for a given knot, you may find the whole family of quivers which produces the same knot generating function. So in this table, I write what are the numbers of those equivalent quivers. By equivalent quivers, I mean different quivers which give the same generating function. You see that for various knots, the number of these equivalent quivers may be quite high. So at first we had just a few isolated examples, so we didn't worry that much, but later on we realized that these numbers are indeed big, and we wanted to understand the structure of these equivalence classes. And the structure turns out to be quite interesting. It is related to this Perimutahidron structure, so I will mention that in a moment. And the important point is that these equivalent quivers are in fact connected by some sequences of permutations of elements of a quiver matrix that we find in some examples. So it's not that these equivalent quivers are completely random, but if you have two of them, you can connect them by a series of just transpositions of matrix elements of a quiver matrix. And these transpositions must be between certain specific elements of a quiver matrix, which satisfy the conditions given in this slide. So this is theorem 6 in this paper that I just mentioned. And one important statement is that these indices A, B, and CD, which correspond to labels of the entries of a matrix that we transpose, these indices are not, of course, they are not random, but first of all, they must satisfy this condition lambda A, lambda B equal lambda C, lambda D, where these lambdas are those monomials that appear in this change of variables that I mentioned before, not in this Notsecure correspondence. So essentially, this indices A, B, C, D tell us which quiver entries we may transpose, and moreover, these entries that we transpose cannot be arbitrary. They have to satisfy these conditions given in the bottom lines. So one of them is that they have to differ just by one, and then there is some extra condition which is a bit more complicated. I will show some examples in a moment, so it hopefully will be more clear. Let me just say that this condition lambda A, lambda B equal lambda C, lambda D can be related to this homological diagram that I mentioned before. And it essentially means that we have to find, first of all, a set of 4 these homological generators which satisfy relevant conditions, and then the quiver entries that we transpose are captured by quadruple of those generators. So this first condition appears from the second order when we compare quiver generating functions for 2 quivers that we are interested in. And those other conditions which tell us that these quiver entries have to differ by 1 and satisfy other conditions that appear in the cubic order. And it turns out that just this quadratic and cubic orders are sufficient to assert that to all orders these generating functions are equal. This follows from certain identity, which follows from so-called multi-cover scan relations, which is presented in this paper by Tobias Heckholm, Piotr Kucharski, and Pietro Longhi. This is another team who is working on this topic. So they have also together a few papers on all of that. So it may be not completely obvious what these conditions mean that I mentioned. So let me just show you some example. If you take figure 8 knot, I again draw in the middle this homological diagram. And the conditions that I mentioned are, in this case, satisfied by this monomials lambda 2, lambda 5, lambda 3, lambda 4. They satisfy this equation in the middle. So the bottom line is that this means that the entry at the position 2, 5, I can transpose with the entry at position 3, 4. So essentially, I have these 2 quiver matrices. On the left side, some of the entries are in yellow. They are, of course, symmetric, so only, let's say, upper triangular part is important. And I can transpose 0 and -1 to obtain the also quiver, which encodes the same generating function. And I summarize this relation on the simple diagram in this case. So this green line corresponds to this operation of transposition. And I have two nodes, white and red, which correspond to these two matrices. I make this picture because these pictures appear also in more complicated situations. So for example, for 5-1 knot, I find if I start with some quiver, for example, the one in the middle here, I find that now I have two possibilities to transpose some elements, either those at position 1, 5, and 2, 3, or at positions 3, 4, and 2, 5. And altogether, I get 3 non-trivial quiver matrices corresponding to the same knot. And it turns out that for more complicated knots, these graphs which represent this situation are quite interesting. Namely, these equivalent quivers arise in families which are labeled by vertices of Perimutahidra. So a Perimutahidron is some higher dimensional polytope whose vertices represent permutations of an object and edges correspond to transpositions of adjacent neighbors. Here you have some examples. Pi1 is of course just 1 point. Pi2 corresponds to transpositions of 2 objects, so this is just a segment. Pi3 corresponds to transpositions between, permutations of 3 objects, and so on. You can draw nicely this nth Perimutahidron in the space of dimension n-1. Here I just have a projection of Pi4 on 2 dimensions. But this is how this Pi4 looks like in 3 dimensions. And this is how Pi3 looks like, of course. So in this picture, each segment has different color, and the color corresponds to a kind of transposition between 2 different, 3 possible pairs of elements that I can make. So we find that these equivalent families, families of equivalent quivers are assembled from Perimutahidras of different size, and we can summarize the structure of each family in this type of Perimutahidra graph, which is made of different Perimutahidra. And you can see it in the non-trivial setting already for 5-2 knot. So in that case, all these equivalent quivers correspond to vertices of altogether 3 Perimutahidra Pi3, which are somehow glued together. For 7-1 knot, you have 2 Perimutahidra Pi3, which are also glued together, and then some extra Perimutahidra Pi2. This is given in the middle of this picture here. And again, each color in this middle picture, each color of a segment corresponds to a different quadruple of homology generators, which encode which transposition we can make. If we consider other 2,2p+1 torus knots, then we get more complicated quivers. So for example, for 9-1 knot, you get this picture. So you see that in the middle, you have 2 Perimutahidra Pi4, then you have Perimutahidra Pi3, and in addition, you have several segments which correspond to Perimutahidra Pi2, and so on. And this is yet another example for 11-1. In this case, we have Perimutahidron Pi5, Pi5, and so on. So for 6-1, we get this structure. So in particular, we get a cube of Perimutahidra Pi4 and then some extra conditions. So analysis of the structure of this equivalence class is quite interesting. So this is another result that we come up with recently. And I think my time is somehow running off. Maybe I will just very briefly say the last result, which is that we can, as I mentioned in the abstract, we can in fact generalize all this to more complicated Calabi-Yaus, because everything I said so far was based on knots, which means that we consider this resolved conifold I started with and some Lagrangian brane in the resolved conifold, but we can replace resolved conifold by more complicated toric diagram. So this resolved conifold from the previous picture you can draw as in this diagram in the bottom here. And this dashed line corresponds to the Lagrangian brane, which we consider which captures properties of some knots. And this is possible to replace this conifold by more complicated toric Calabi-Yau geometries, what we did, we considered the families of these geometries which do not have compact 4 cycles. So they can be obtained by a triangle. I mean, their diagrams can be obtained by triangulation of a strip. For this reason, they are also referred to as strip geometries sometimes. So in that case, we can also compute partition functions of some branes. In particular, for a specific framing, these partition functions turn out to be Q-hypergeometric functions. As you see, they depend on some parameters which I call alpha and beta. And these alpha and betas, they essentially encode Kähler parameters of those geometries. So our main statement is that these partition functions can also be written in this quiver form, like in this middle line in this slide, namely this psi, which is this open string partition function, can be written as quiver generating function PC for appropriate quiver with appropriate identification of variables. So this result tells us in particular that corresponding BPS invariants, which in this case are quite analogous to the LMOV invariants I mentioned above, are also integer. And using some results from some of these previous papers, we can even write classical version of this invariant, this classical omega. Very explicit theory. So you see these omegas are given by these sums, but those sums have certain non-trivial denominators, but nonetheless they should be integer. And this relation to motivic Donaldson-Thomas invariance tells us that they are indeed integer. And this statement, at least in some special cases, was confirmed also by some number theorists, like in this paper mentioned here in the bottom, where they proved using number theory formalism or certain approaches from number theory that indeed the numbers that we obtain in this way are integer. So I think this is all I could say. This is a brief summary. I just hopefully showed you that this Notsecure correspondence, which relates knot theory and the representation theory, is hopefully somehow interesting. This is motivated by string theory and also makes contact with several other areas, which hopefully could be of interest to some of you. So thank you very much.
Thank you very much for telling us about this very interesting topic. Any questions? So when you say that two quivers are equivalent, do you just mean that they have the same motivic DT invariance, or the stronger condition?
No, they have different motivic DT invariants, but when I relate them to knots, I need to identify those generating parameters xi somehow. So upon this identification, these combinations of their DT invariants are the same, but not all these individual invariants.
I see. Then what is exactly the algorithm to generate all these equivalent quivers?
Well, if we know, if we are able to find one quiver, then we have these conditions that I mentioned. So we can look at entries of this quiver matrix and look when these conditions are satisfied. When they are satisfied, we can make transposition of 2 elements. So we obtain another quiver matrix. And we can repeat it finite number of times and generate all this family, which is parameterized by vertices in this Perimutahidron graph, which I showed.
I see.
So we put it in a computer. I mean, in Mathematica, this is also attached to the paper on archive. You can download if you want, and you can plug any quiver matrix you want, and it will find for you all those equivalent matrices and even make some nice pictures of those.
I see. So, any other questions? So if not, let's thank Piotr again.
Yeah, thank you again. Maybe I just stop showing.